So welcome to lecture 2, and we'll just start with a little recap for what we covered last week. So let me move this here to full screen. So last week we kicked off the class with some basic introductions to why model-based meta-analysis is important, as well as the beginnings of some introduction to traditional meta-analysis, talking about the background in terms of the importance of planning your meta-analysis. And then we covered a little bit of the statistical models for a fixed effects meta-analysis, both the frequentist and the Bayesian topics. So today we're going to pick up at the very end of that topic, talking about a little bit about what we can do when the standard error isn't reported for the models that we're trying to fit. If you recall, one of the important elements of the analysis was that we had some measure of elements of the data that we needed to do the analysis was not only the outcome measurements, but we also needed some measure of that standard error. And we talked about how ideally we'd like to have the actual measure of standard error itself. But if we didn't, what we might think of as how we might replace that with using the sample size. But there are other ways if we can make a little bit more effort, we can actually extract information about the standard error from various pieces of data that might be reported in the papers that we're using for our analyses. If the endpoint that we're working with is continuous, so if in the examples that we looked at previously, if we were talking about a log odds ratio for a responder rate, for example, or a mean difference from placebo, then we can extract the standard error either using confidence intervals for that difference or for the mean effect, and we'll give an example about how we can extract those from standard errors from confidence intervals in just a minute. If we have the standard deviations for the two treatment groups, we could just mathematically calculate the standard error for the difference between those two groups. If there's a t-statistic comparing the two groups, or even a p-value from that t-statistic or t-test, we could derive the standard error. Or if you have some studies that do have standard errors and others that don't, you could even imagine fitting a model to impute those standard errors. And we will look at an example of that later when we get into the model-based meta-analysis portion of the course. There's a paper by Folman and colleagues that was published in 1992 in the Journal of Clinical Epidemiology that gives details on all of these methods. But I thought we might imagine looking back at, or looking at an example, a real example that was published, and thinking about how we might apply these methods to extracting standard errors. So recently this year, there was a paper published on the effect of ramipril on walking times and on the quality of life. The effect of ramipril on walking times and quality of life among patients with peripheral artery disease. It was published in JAMA. And in that study, they had 212 patients, and they said the following, that at 6 months relative to placebo, ramipril was associated with a 75-second increase in mean pain-free walking time, p less than 0.001. And they provide a confidence interval for that difference from placebo, saying it goes, a 95% confidence interval range from 60 to 89 seconds. So they don't actually report directly a standard error for that mean difference of 75 seconds, but either from the confidence interval or from the p-value, we can estimate what that standard error is. So from the confidence interval, we know that the confidence interval, assuming they used a t-test, or what would be the estimated difference, which is 75 seconds, plus or minus the corresponding t statistic times the standard error. And so if we do a little bit of math, we can derive that the standard error for the difference is equal to the upper limit of the confidence interval minus the lower limit of the confidence interval, divided by 2 times the appropriate t statistic. So in this case, it's a 95% confidence interval, and we have 212 patients. So we're estimating 2 mean values, one in the ramipril group and one in the placebo group. So we would take the t value from a t distribution with 210 degrees of freedom, so that's 212 minus 2, and at a percentile of 0.975, corresponding to a 2.5% upper tail of the t distribution. So when we plug all those in using the values we have from our study here, we have the numerator is 89 minus 60. That comes from our confidence interval. And our denominator here is, or this t statistic in the denominator is 1.971. And if we finish the calculation, we get an estimated standard error of 7.36. Now, if they hadn't provided the confidence interval, we could have tried to calculate a standard error simply based on this p-value. They don't give us an exact p-value, but they tell us that the p-value is less than 0.001. So we could assume that the p-value is equal to 0.001 to get an upper bound on what that standard error might be. And again, just inverting the t-test, that would give us this p-value. We can get a formula that says that the standard error of the difference is equal to the difference divided by, again, this t appropriate quantile of the t distribution. In this case, we'll rather than plugging in a 0.975 here, we would plug in whatever our p-value is. In this case, we're going to assume to get this upper bound that is 0.001. So we would take divide by the quantile of the t distribution, that's 1 minus 0.0005, that's 0.001 over 2, with 210 degrees of freedom. So you can see that that's a much larger t-value of 3.34 compared to the 1.971 above. But when we do the math, we can get an upper bound of the standard error of the difference being 22.5. So clearly that p-value, we have a much better estimate, and in this case we would use the one from the confidence interval. We have a much better estimate of the standard error being 7.36. But if in the absence of that information being reported, we could have said, well, we at least know the standard error of the difference is less than 22.5. So in this case, we're able to get pretty good estimates from the confidence interval. That's for continuous data, and I think it's fairly straightforward how to approach that. And actually, for those kinds of estimates, more often than not, we do get measures of standard error. If we're working with binomial data, and the treatment effect is a log odds ratio or a relative risk or a risk difference, we can actually rely to some extent on asymptotic variance of the log odds ratio or the relative risk or the risk difference, being a function of the number of events in the arms that we're comparing. So for example, for the log odds ratio, it's the asymptotic variance of the log of the odds ratio is equal to 1 over the number of events in the active arm plus 1 over the number of non-events in the active arm plus 1 over the number of events in the control arm plus 1 over the number of non-events in the control arm. And then from that we could derive the variance of or the square root of that would be the standard error of the log odds ratio. So that's a fairly straightforward and simple approximation to the variance of the log odds ratio. And as we'll see later, typically we'll do meta-analysis of data of binomial data on the log odds ratio scale, but then report it transformed back to the odds ratio scale. So what's typically of interest is that variance of the log odds ratio. Of course, if we had a confidence interval again or a p-value for the odds ratio, we could similarly derive an approximate standard error for the odds ratio or log odds ratio from those using the methods for continuous data. And finally, if we're working with survival data, typically, if we're working on treatment effect measures such as a hazard ratio, we can again use confidence intervals, p-values from a log rank test. If it may be the case that in some journals you may have estimates of survival at different time points, and there may be a Kaplan-Meier curve plotted with confidence intervals, we could extract the confidence interval measure from that as well. For survival data, there's an excellent article by Parmar and colleagues published in 1998 in Statistics in Medicine that covers ways to extract information about the standard error from summary statistics to perform meta-analyses. So we touched on this briefly during the last class, but what if we have this continuous response, can we just use a sample size rather than the standard error and just sort of forget about using this, trying to extract all of this extra information? And the answer is that we can, but we have to, in the process of doing that, we'll be making a number of assumptions. And there's one that's very important and fundamental to that analysis. And even if we, so I think the questions you want to ask yourself in doing that are, what are those assumptions that we're making? And are those reasonable assumptions? And if we can extract the standard error, is it reasonable to make those assumptions? So if we go back to the original model and think a little bit about the math, if we're simply using the sample sizes, we know that the sampling variance of the mean is equal to the sampling variance of the observations divided by n. If we're thinking now about not thinking about an effect size, but simply thinking about measuring a mean response, for example. Then we could replace the variance of these epsilon i's here with a sigma squared I over ni. In the absence of information about the sigma squared I, you can imagine that we may assume that the sigma squareds, the variance of the response in each study, are all the same. And we showed last time that collapses into a simple estimator that depends only on sample weights relative to sample size rather than to standard errors. So in the process of doing that, the fundamental assumption that we're making is that this residual variance, or the sampling variance of the response, is the same in all studies. And that may or may not be a reasonable assumption to make in any particular analysis, but it's something that if we are simply basing our inference on sample size rather than standard errors, we need to consider. My opinion is that particularly when we're doing these simple meta-analyses or the traditional meta-analyses, we should always rely on standard errors to the extent that we can derive them, or of course standard deviations if we can derive those, to base our inference on using the standard errors rather than simply using sample size. Because I think for most applications where we're using traditional models, we'll be able to get that information for the endpoints that we need. So let's look at an example of performing a fixed effects meta-analysis. And what I have here are data from 8 randomized controlled clinical trials of Atorvastatin, Atorvastatin 10 milligrams. And the data themselves are the percent change from baseline LDL. So we have the mean difference between 10 milligrams of atorvastatin and placebo across these 8 trials. From each of those, we also have a standard error that's been reported. We can see in the 8 trials, the mean differences range from a difference of 48.6% to 33.8%. And some studies have very small standard errors. So this 981-8 study has a standard error of 1.1. As compared to other studies, the 981-96 study, for example, has a standard error of 4.88, so about fourfold higher. So from our standard errors, if we're going to perform a fixed effects meta-analysis, we would calculate the weights, which is 1 over the squared standard error. And that's presented here in the fourth column. And just to make comparisons easier, what I've calculated in the last column is the relative weight, which is simply each of these weights divided by the sum of the weights. And so we can see, for example, that the study 981-8, that has the smallest standard error, clearly gets the largest weight. In this case, the relative weight is 40.475. So in that analysis, in that weighted average, nearly 48% of that particular study's mean difference of minus 37 will get about 48% of the weight in that weighted average. And we can compare that to the smaller study, the 981-96, that gets a relative weight of only 2.5%. So in this case, we have quite a variety of weighting factors that are coming into play in this particular analysis. And so if we plug into the formulas that we had in our previous lecture, the fixed effects meta-analysis estimate of the mean difference from placebo is the sum of the weights times the differences divided by the sum of the weights. And in performing that calculation, we come up with an estimate of the difference from placebo of 37.2%. And to get our standard error estimate, we would say that the standard error of that fixed effects estimate is the square root of 1 over the sum of the weights. And if we were to plug in these weights here in the second to last column, add those up, take the inverse square root of that, we see that the standard error is 0.771. So putting those two things together, we can get an approximate confidence interval using a normal approximation or a walled confidence interval of minus 38.7% to minus 35.7%. So the fixed effects meta-analysis itself, as we can see, is very, very simple to perform, even by hand. And as we'll see later in the session today, it's even easier to perform with some simple R functions. This is a plot of the data from those 8 Atorvastatin studies. And this is called a forest plot, and we'll see later today how to make these. This is the classic forest plot will have really two primary elements to it, along with some labels. The first primary element are these plots of the data themselves. So in this representation, we're plotting the data as squares, and the size of the square is relative to or inversely proportional to the standard error, or proportional to the or roughly proportional to the weight that it's getting in the analysis. So larger squares represent studies that are getting more weight. And the whiskers here are 95% confidence intervals. So correspondingly, estimates that have small confidence intervals get big squares because they're getting more weight, or because they have smaller standard errors than studies with long confidence intervals. The second major element is some measure or plot of if you have it, of the estimate from a model. In this case, what we're showing here on the bottom is the estimate from the fixed effects model. And in this representation, we plot that as a diamond with the center of the diamond lying at the estimated effect, where the effect is, and the points of the diamond horizontally extending to the lower and upper bounds of a confidence interval. In this case, it's a 95% confidence interval. And then we've augmented this particular graph with some labels here on the left to describe what the study names are, and over here on the right that give us numerical representations of the mean difference and the confidence interval limits. And this is the standard kind of default plot that we can make in R very easily using the metaphor package. So let's look at a second example. The first example was one that used continuous measures. This example will look at one that uses binomial, has a binomial endpoints, and we'll look at the meta-analysis on the odds ratio. So we introduced this earlier in this course when we were looking at examples of meta-analyses. This, just to recap, though, this is a meta-analysis that was published through the Cochrane collaboration in 2006, and their objective was really to assess the effect of chemotherapy and radiotherapy in inoperable advanced pancreatic cancer. We're going to fit a meta-analysis model to a subset of the studies that they looked at. We're going to focus specifically on the 6-month mortality incidence, and for that endpoint, they had data from 14 trials. And more specifically, we're going to focus on the comparison of gemcitabine plus chemotherapy to gemcitabine alone. So here's a forest plot of that 6-month mortality incidence. And what we're plotting here is the odds ratio. So on the horizontal axis here, we're plotting this on the log scale. So this horizontal or this vertical dashed line is at the value of 1. So that would be an odds ratio of 1 means there's no difference in terms of mortality incidence between the combination therapy versus the gemcitabine alone therapy. Odds ratios less than 1 favor the combination, and odds ratios greater than 1 favor the monotherapy. And so in this plot, we've augmented the typical plot with an additional column of information here called chemotherapy. This is what the background chemotherapy was that patients were receiving in addition to gemcitabine. And we'll come back to looking at that later when we talk about meta-regression and trying to explain what might be causing some of the underlying between study differences in these results. So here are the data presented in a tabular fashion. Again, with the first column being our study, the second column being the odds ratio. And in this table, what I've done is I've ordered them from lowest odds ratio to largest odds ratio. The third column is just the log of that odds ratio. The fourth column is the standard error for the log odds ratio. And here this is simply calculated using the formula that we talked about previously, because what was presented in the summary tables was the number of patients who were enrolled in each treatment arm and the number of patients that had died by month 6. So for each study, we're able to form a small 2x2 table and calculate the odds ratio and the standard error of that log odds ratio. The second to last column here is their weight, similar to what we had in the previous analysis. And the last column here is a relative weight. Again, the weights divided by the individual weights divided by the sum of the weights. So what's interesting in this particular analysis is that there's less heterogeneity in the relative weights. That is, we don't have any one study that's dominating the analysis. But we have a number of studies here that are getting on the order of 10 to 15% of weight. And we do have a couple of small studies here that are getting less than or about 1% of the weight. And what's interesting is that the two studies that are getting the smallest weight, or many of the studies that are getting a small amount of weight, are actually the studies that show the largest effect of the gemcitabine plus chemotherapy. Whereas the studies that are getting the larger amounts of weight are the studies that tend to be showing that there's no difference, or if there is a difference, it's going in the opposite direction. So let's perform our analysis here on the log odds ratio. And in this case, we're treating the log odds ratio as continuous. So we're going to take our standard formula for the fixed effects estimator and simply kind of plug and chug. And if we do that, we get an estimate of the log odds ratio of minus 0.115, with a corresponding standard error of 0.071. So remember, those are on the log odds ratio scale, so we can back calculate those to the odds ratio scale by exponentiating the estimate. So we get an estimate of the odds ratio of 0.89 and a confidence interval for the odds ratio of 0.78 to 1.02. So this would say that there's about the odds of mortality within 6 months on chemotherapy relative to chemotherapy plus gemcitabine relative to gemcitabine alone are 0.89, with perhaps some evidence that there is a mortality benefit, statistically significant mortality benefit. With this confidence interval here just creeps over the value of 1, or that null value. So that's our examples of traditional meta-analysis. Here's our forest plot of that. Again, ordered now here a little differently than it was shown previously. This is ordered in terms of biggest effect to smallest effect, and with our fixed effects estimate shown here as the diamond. So I think I'll stop there and ask if there are any questions about either of those two examples. And okay, well, if there are no questions, we'll just move ahead. What we've talked about so far is that traditional fixed effects estimator of, in the case of binary data, taking the estimator on the log odds ratio scale and performing that simple kind of weighted average approach. And as we saw previously in this last example, the fixed effects meta-analysis estimator of the odds ratio is really a weighted average of the log odds ratios from the individual studies, and then we exponentiate that to get an estimate of the odds ratio. If you remember back to any of your early statistics classes or biostatistics classes, you may have talked about estimators of combining 2x2 tables using something called the Mantel-Haenszel estimator. And that's a kind of estimator where you might stratify on different levels of a covariate, for example, and then calculate an odds ratio within each of those strata and then try to combine them across strata. In the meta-analysis context, our strata are really different studies. And what we're thinking about doing is taking an odds ratio measure from each study and then using the Mantel-Haenszel approach to combine them across studies. And in fact, you can think about the Mantel-Haenszel estimator as really a weighted average of the odds ratios, whereas that fixed effects estimator I presented earlier was really a weighted average of the log odds ratios. So to get the Mantel-Haenszel estimate, what we would do is calculate the odds ratio in each study. So if we think about this as a little 2x2 table, and we have groups in the rows and response, or in the example of the pancreatic cancer, we had the dead or alive in the columns. And if we just label those A, B, C, and D in the 4 cells of that 2x2 table, then the estimated odds ratio from that study is just A times D divided by B times C. And if we think about I'll just say that the Mantel-Haenszel odds ratio is the estimator itself is simply this formula here towards the bottom. That's the sum of the A times D divided by Ni for each study. That quantity divided by the B times C over Ni for each study, where Ni is simply the sum of the total number of patients in that trial. And you can think about that if you do a little bit of math. You can show that this is simply a weighted average of the study-specific odds ratios, where those weights are equal to B times C over N. If you think about that if you were to plug in this WI and take the psi i's here as our odds ratios and go back to that fixed effects estimator formula where it's just that weighted average, that's what you derive exactly this psi hat MH, or the Mantel-Haenszel estimator of the odds ratio. There are several different estimators for the variance of the Mantel-Haenszel, of the log of the Mantel-Haenszel odds ratio. I'm not going to go into them here because we're not going to spend much time thinking about the Mantel-Haenszel estimator. But you can derive those in several statistics packages. We'll provide those for you. But there are some cases where the Mantel-Haenszel estimator is actually the one that you would want to use. And in particular, that happens when you're working with very rare events. If you have a situation where there are no events in one of the treatment arms, it turns out that the standard estimator discounts that study entirely from the meta-analysis. And the reason that is because, I'll back up here to the formula for the variance of the log odds ratio. So we focus here on this formula in the middle of the page. If we had no events in a particular study, let's say in treatment arm A, then this NA would be 0. And the variance of the log odds ratio would be undefined, but it would be infinitely large. Because this would be have included a term that would be 1 over 0. And with that weight, that variance being infinitely large, the weight of that study, which is the reciprocal of that variance, would be 0. So any study that has a treatment arm that has no events in it is actually, with a classical fixed effects estimator, ends up being excluded from the analysis. So there's been some proposals to take an ad hoc solution by simply adding a half to each cell in the 2x2 table. And you do sometimes see that approach taken. And then using the classical fixed effects estimator for the log odds ratio. However, for the Mantel-Haenszel estimator, if we have a 0 in either in any of these cells, we can see that that particular study may drop out of the numerator or denominator, depending on where the 0 is, but it won't drop out of the estimator entirely. So there's one benefit to the Mantel-Haenszel estimator. If in fact you have no events in a study in its entirety, then both the Mantel-Haenszel estimator and that classical fixed effects estimator end up excluding that that study from the analysis altogether. And again, that's because the weight for that study is 0 in either case. It's probably clear why that happens for the fixed effects estimator. If we think about this in the case of the Mantel-Haenszel estimator, it'll turn out that if either A or B if A and C are equal to 0, that is no events in the study entirely, then this weight here will be 0, and that study will drop out of the meta-analysis. So if you're working with rare events, you probably want to think about using the Mantel-Haenszel estimator, or in fact, there are alternative approaches using Poisson regression that were discussed in a paper by Tianxi Kai and colleagues in 2010, which are probably even more relevant and useful in the context of rare events. And I think we may come back to that if we have time toward the end of the class and talk a little bit about that alternative approach. And before you think it's sort of a meaningless thing to think about when you're, if you think back to the late 2000s, or I think it was around 2008 or 2009 when there was a large meta-analysis of mortality from rosiglitazone. There was a lot of controversy around the results of that meta-analysis in part because there were about, I think, 40 studies or so included in the meta-analysis, and a large fraction of those, upwards of 30%, had no events. And so in the analysis that were performed, those events drop out, and whether or not you include them or not, depending on which kind of estimator you use, can influence both your estimate of the effect of rosiglitazone on mortality, as well as and other cardiac events, as well as how certain you are about that estimate. That is how wide your confidence interval is. So when you're working with rare events, the type of estimator you use can have a meaningful impact. However, in practice, if you're not working with rare events, if all of your treatment arms or studies have events in them, then there's really not much of a difference between that classical fixed effects estimator and the Mantel-Haenszel estimator. Just to wrap up the discussion of the Mantel-Haenszel approach, we're talking now about fixed effects analysis. We'll move soon into talking about random effects meta-analysis models, and it's really not clear how to extend that Mantel-Haenszel framework into random effects models or even meta-regression models, where we might be trying to describe what's causing any differences between studies. And so while the Mantel-Haenszel estimator is useful, it in and of itself is a somewhat limited use if we're trying to get into more sophisticated models. Okay, I think we've really covered this part. I think rather than going straight to talking about how to fit these models in R, what we'll do is we'll have a discussion about random effects models, and then we'll just do all of that together at the end. So to this point, we've assumed that each of the studies is estimating one common effect, and we've just been using the Greek letter theta to denote that effect. However, if there is heterogeneity in that effect between studies, that is, if each study kind of is estimating its own treatment effect, and then there's some additional sampling variability around that treatment effect, we're in a situation where there's heterogeneity of effect between studies. And in fact, we should really expect there to be heterogeneity of the treatment effect because we're more often than not pooling studies that are really diverse, both in their trial design, meaning the patients that are included, maybe the duration of treatment, perhaps the background treatments that are being administered, maybe dosing regimens if we're not doing a model-based analysis, as well as when endpoints are measured and other things like that. So there's a lot of these kinds of elements that can contribute to the fact that each study might be having a different expected treatment effect than other studies. And there are ways to try to measure that. There's really two that are, or I'll say three that are used somewhat broadly. The first is Cochrane's Q statistic, and that's a measure that we'll see that's derived by inverting a chi-squared test that has been used historically quite extensively. However, more recently, meta-analysts have switched to using the I-squared statistic, which tries to get at a more intuitive and descriptive measure, and a measure that is comparable across meta-analyses. And lastly, if we're performing a random effects meta-analysis, we'll see we can estimate the between study variance, and we could consider using that as a measure of heterogeneity. There's a fourth measure that's called the H statistic, which it's not used very often, but if you come from a very quantitative bent, it does have some nice quantitative properties that can relate to certain kinds of plots that we'll see later. So what we'll do next is we'll kind of step through each of these in turn and talk about how they're derived and what their pros and cons are. So the Q statistic is simply a weighted sum of squares of the deviations of individual study estimates from the overall estimate. So mathematically, what we do is we take the observed theta hats. So these are, say, the differences from placebo. We subtract off our fixed effect estimator. We square those and then take a weighted sum of those, where the weights are those fixed effect estimator weights we used in the meta-analysis to begin with. And it can be shown that if there's no heterogeneity, so that if each of those studies is estimating the same treatment effect, then this statistic Q follows a chi-square distribution with r minus 1 degrees of freedom. And here r is the number of studies that we have. And you can use this fact to perform a test, to test whether or not there's any heterogeneity. Simply comparing the observed chi-square statistic to a chi-square distribution with r minus 1 degrees of freedom. The problem is that those tests and that Q statistic the tests aren't useful, and in fact the Q statistic itself isn't particularly useful outside the context of the meta-analysis that you're performing. So the test isn't useful because when you have a small number of studies, that test actually has very low power. So if there's heterogeneity, you'll be unlikely to detect it when it exists. And when you have a lot of studies, it actually has a lot of power, which means that if there's even a little bit of heterogeneity, you can come up with a statistically significant test based on the Q statistic. So you might be inferring that there's a lot of between study heterogeneity, when in fact there's only, or not that there's a lot, but that there's a statistically significant amount of heterogeneity, even though it's a very small amount. The other downside to the Q statistic is that it can't be compared across meta-analyses. So if I've performed a meta-analysis in one disease area, and you've performed a meta-analysis either in the same disease area using different studies or in a different disease area, we can't compare those because the magnitude of the Q statistic is going to depend on which studies are included in terms of what their estimate of the overall effect is, as well as simply the fact that, as you add more studies, your Q statistic is going to get bigger and bigger because you're taking the sum overall of the studies. So the Q statistic can't be interpreted in and of itself in isolation, or I'm sorry, it has to be interpreted in isolation. It can't be compared across meta-analyses. Now, nonetheless, this statistic has been used largely in many meta-analyses that were performed prior to, 2005 or so. Around 2005 is when we started seeing this transition to using the I-squared statistic, which was proposed in a paper by Higgins and Thompson in 2002. And so I-squared, the reason that Higgins and Thompson started to develop this statistic was because of the issues that they perceived with Q. And so their primary goal was to come up with a measure of the degree of inconsistency across studies. And if you read their paper, you'll see that they evaluate several different candidate measures, but the one that they recommend is this measure I-squared, which they give an interpretation as the percentage of the total variation that's due to heterogeneity rather than chance. This notation is a little bit premature, but as we get to talking about random effects meta-analysis, it'll make a little bit more sense. This I-squared statistic is simply this tau squared, which is our between study variability, divided by the between study variability plus a measure of the sampling error, the sampling variability, or some measure of so that those two elements combined give us the total amount of variation. So this gives us essentially the between study variation divided by the total variation, and then expressing that as a percent. And if we have if we've calculated the DerSimonian and Laird estimator of tau squared, and we'll see what that is in just a minute, then we can express I squared, in fact, as a function of the Q statistic. So I squared is going to be a value then that ranges from 0 to 100, has a nice interpretation that can be easily understood, as well as compared across meta-analyses. One of the downsides, though, is that there aren't really any tests based on I squared. So we can't say there's not a test that would say test I squared, the hypothesis that I squared is equal to 0. You could imagine deriving those perhaps based on asymptotic approximation to a sampling distribution for I squared, or maybe some sort of, that's probably the best thing you could do. But that actually hasn't really been pursued very much because I squared is really meant to be a descriptive measure rather than something that's a quantitative statistic that's used for testing. In their paper in the British Medical Journal, Higgins and Thompson propose a rule of thumb in terms of interpreting I squared, where values that are less than 25% are an indication of low heterogeneity or low between study variability, and values of over 75% correspond to high between study variability, and values in between are sort of a moderate amount of between study variability. But that's kind of the best that you get in terms of any kind of rules of thumb for how to interpret I squared. So I think I've covered at least the first bullet, the fact that I squared is preferred to Q because of its intuitive interpretation. Also the fact it doesn't depend on the number of studies that you've incorporated or what your endpoints are, what your effect measures are. There are confidence intervals we can calculate for I squared. And as I said before, you can compare them across meta-analyses. So we'll show a little bit later on, or perhaps when we get to the hands-on exercises, how to calculate a confidence interval for I squared. It's probably best and easiest simply to rely on software packages to do that for us, and we'll see how to extract those from Metaphor. In that paper where Higgins and Thompson proposed the I squared measure, they also have proposed a statistic called H. It's one that they decided to discount, and however, as statisticians, they rather liked it because it does have nice statistical relationships. But as practicing statisticians, they realized that it didn't have any clear intuitive interpretation, so it would have a limited benefit. But for anyone who's interested, H squared, they define as the Q statistic divided by its degrees of freedom. So from a statistical perspective, that's simply the relative excess in Q compared to its expectation, keeping in mind that the expectation of a chi-squared random variable is its degrees of freedom. And it also has a kind of a nice connection to the radial plot that we'll talk about later in the probably next week, in that H is the residual standard deviation from a radial plot. So it's got these kind of cool statistical qualities to it, but it's really its practical use is limited because it's hard to describe and doesn't give a nice intuitive interpretation. The tau squared measure, which is our residual variance in our random effects meta-analysis models, is also something that we see published frequently, but in terms of it is a good measure of the extent of heterogeneity, but it can't be compared across treatment measures, can't be compared across different meta-analyses, and isn't in and of itself a measure of how much impact that the between study variability has on the analysis itself. It'll be a useful description that I think should be paired up with I squared, but simply presenting it by itself isn't necessarily that useful of a description. So let's take our data and do a little bit of work to understand what sort of heterogeneity we have in our LDL data set. So if you think back to that example where we looked at 10 milligrams of Atorvastatin versus placebo, our endpoint here is % change from baseline LDL. We calculate our Q statistic. We simply plugging into the formula here, we end up with a Q value that's 15.61. And under the null hypothesis of no heterogeneity, this Q should follow a chi-square distribution with 7 degrees of freedom because we have 8 studies. And so if we were to compare this value of 15.61 to a chi-square distribution with 7 degrees of freedom, we'd come up with a p-value of 0.029, which would indicate that there is statistically significant heterogeneity in the effect. So telling us that there is some between study variability in that the effect of atorvastatin relative to placebo. Similarly, we could, if we wanted to, calculate H. For the purposes of this class, I'm not going to dwell on that because H is not a statistic that we'll be focusing on going forward. But we can also calculate I squared, which turns out to be 55.1. So this would tell us that about 55% of the total variability in those differences from placebo is due to between study variability rather than due to chance. Okay. And as I pointed out before, we can get confidence intervals for I squared, and we'll look at how to do those in R in the second half of the class today. So why don't I pause there and see if there are any questions on these measures of heterogeneity. So we have one. When considering heterogeneity, do we assume individual studies are a sample of studies as opposed to using only studies of interest? That is, classical definition of random effect versus fixed effect. I think the answer there is yes. We're thinking about these as these studies as sort of a sample from a population of studies. I think you can clarify me if or I guess this would be a sample from a population of, because they're conceptual studies. If you believe that we've collected all the possible studies that there are for this particular comparison of interest, you may say that we've kind of exhausted the entire population. But I think in this case, we're thinking about the sampling distribution of this. If we're thinking about the Q statistic, for example, the sampling distribution of that is kind of under the assumption that we're getting these repeated samples of studies of 8 studies from a sort of a hypothetical population of studies. I hope that helps answer your question. If not, feel free to clarify. Okay, you're welcome. What we're going to do next is we're going to get into the random effects meta-analysis model, and I'll do that, and then we'll work on that for about 5 or 10 minutes. That'll get us up to a good stopping point, and then we'll take a short break. So the random effects meta-analysis model is a very simple extension of that fixed effects meta-analysis model. And just as before, we're going to let theta denote the measure of treatment difference, and theta hat I, the estimate from the ith study. And using that notation, then the general random effects model is of this form here, where our model is that theta hat I equals theta I plus epsilon I, where the theta i's, which are the study-specific, true study-specific effect in the ith study, themselves follow a normal distribution centered at this overall mean effect theta with between study variance tau squared. And just as before in the fixed effects meta-analysis, we're treating the variance of the epsilon i's as known and equal to the estimated variance of the theta hat i's. So this is our model. This is, if you're used to population modeling, then this is a sort of simple and probably natural extension to that fixed effects model. So we can show that if tau squared were known, so if we knew the between study variance of the effects, it's pretty straightforward to show that the maximum likelihood estimator for theta, that is the average effect, is itself a weighted average, where we're using different weights. I've denoted those by W star here. Those weights are equal to 1 over the SI squared, that's our observed standard error, plus tau squared, which is the between study variance. And that the variance of that random effects meta-analysis estimator is equal to 1 over the sum of these random effect meta-analysis weights, the WI stars. So in fact, if we knew tau squared, really this problem becomes no different than what we were doing before, because we're in fact using the same formula but with different weights. The problem though is that we don't really ever know tau squared, and so we need to estimate tau squared. And there's a number of different ways to estimate tau squared. Probably the most popular one, or at least the one that has been used historically the most, is a method of moments estimator that's attributed to DerSimonian and Laird. And we'll talk about that in just a minute. More recently, though, you see people using more oftentimes some sort of maximum likelihood or restricted maximum likelihood estimator. But the basic idea is you use those approaches to get your estimate of the between study variance tau squared, and then you're plugging into this maximum likelihood estimator for your overall random effects estimator. So DerSimonian and Laird did something very interesting in their paper. They said, let's equate the Q statistic to its expected value, and then invert that to come up with an estimator for that variance component tau squared. So that's in statistics, that's classically known as a method of moments estimator. And when you do that, you come up with this estimator here in the middle of the slide. The DerSimonian and Laird estimator of tau squared is the maximum of Q minus its degrees of freedom divided by this function of the weights in the denominator, where those weights are the fixed effects weights. That is 1 over SI squared. And if that value turns out to be negative, that is if Q is less than its degrees of freedom, then you just say that the between study variance is 0. So it's a very simple closed form expression, and I think that's really the main reason why it's been popular, because it's very easy to calculate given your fixed effects analysis. So essentially you perform a fixed effects analysis. From that you get your fixed effects weights, the W's, you get the Q statistic, then you use those things in combination to calculate tau squared, and then you can update your analysis to get the random effects estimator of the overall mean effect. If in performing this analysis you're interested in getting a confidence interval for tau squared, there are at least 2 approaches. One that gives you a symmetric interval that's based on a large sample approximation to the distribution of the variance of tau hat squared, or you can use a gamma distribution to get an asymmetric interval. And again, we'll see. We won't go through the mechanics of calculating those, but we'll be the beneficiaries of the fact that that's already been programmed for us in the metaphor package. That's the DerSimonian and Laird estimator. If instead you're interested in getting a maximum likelihood estimator, and probably not surprisingly to you, those are not available in closed form. But of course, if you have software for fitting meta-analysis models or fitting kind of general mixed effects models, and you can use those tools to get the maximum likelihood or restricted maximum likelihood estimators. For the purposes of this class, we're going to focus on using the metaphor package. And I see I have a typo here. This PH, this is my spell checker correcting me when it shouldn't. This PH actually should be an F. So the metaphor is METAFOR. And those are probably the estimators that we'll rely on most when we're doing our analyses going forward, because they're going to be the most easily translatable or comparable to the approaches that we'll take when we move into model-based meta-analysis approaches, where we'll really be relying heavily on maximum likelihood estimation. As it turns out, we've got these different ways of coming up with estimators of tau squared. I've mentioned 3 here. There are actually many others that I won't mention. But if you have a lot of studies, it turns out that the practical differences between these are small. So really your estimates of tau squared are going to be similar regardless of the estimation method that you use. Although there will be times when you may get a maximum likelihood type estimator that's bigger than 0, but the DerSimonian and Laird estimator gives you an estimate that's equal to 0 because the degrees of freedom are bigger than the Q statistic. So that's estimation. That's random effects meta-analysis. It's a very simple direct extension of the traditional fixed effects approach. We can obviously couch all of this in a Bayesian framework as well. And all that we're doing in this case is really adding one more level to that hierarchical model. So we have in the frequentist setting, we have our model for the data, which is the theta hat is equal to theta I plus epsilon I. We have a model for the theta i's, between study-specific thetas. And then in the Bayesian approach, we're going to put another level of model on the theta and on tau squared. That is, we're putting prior distributions on those parameters. And that's what this slide shows. We have our model for the data. That's going to say something like the theta hat i's, given the study-specific effect and the sampling variance, follows a normal distribution with mean theta I and variance SI squared. Then the next level of the model is for the study level parameter models. That is, the theta i's conditional on the overall mean and between study variance follow normal distribution with mean theta and variance tau squared. And then we put some prior distributions here on theta and tau squared, and I'm just generically denoting those as F and G. But one example might be we might use a normal prior distribution for theta and a uniform prior distribution for tau. That is, a uniform prior distribution for the between study standard deviation. You might instead use an inverse gamma distribution for tau squared. And we'll come back and look at an example of how to fit these models. One thing that you might note here that's different than in the fixed effects model is in the fixed effects model, it was very simple to put together a conjugate model. So we were able to derive analytically what the posterior distribution is for theta. And there are combinations of priors that we could use here to give us something that gives us conjugate posteriors for theta. And if that's something that you're interested in, we can talk about that during the lab session on Monday. Feel free to let me know. What we're going to use, though, is this model. We're going to take advantage of this opportunity to show how to fit these kinds of models in WinBUGS. Okay, we're going to pause there and come back to wrapping up our meta-analysis piece with talking about the sort of relevant aspects of meta-analysis and things to keep in mind, and then going through a little example for the data that we have. And then we'll finish up the rest of today's class with a demonstration of how to use metaphor to do these analyses for us, and that'll set you up for the first homework assignment that we'll provide to you later in the day. So I think what we'll do now is we'll take a short 5-minute break to give you guys a chance to stretch your legs and and we'll come back in 5 minutes. I think what I'll do though now is we'll set up, just to keep everybody kind of on the same wavelength. We'll start a timer here. We'll set a timer for 5 minutes, and when that's up, we'll restart. All right, well, I guess we'll get started, restarted. If you had any thoughts about questions while you were taking the break, please feel free to post them in the questions, as we'll take a break again to see if you have any questions as we finish this section before we start the demonstration. So we're talking about random effects meta-analysis. And simply fitting the models, as we saw, really wasn't much more complicated than in the fixed effects case, particularly because we have software that's available to us to do that. But as we're performing a random effects meta-analysis, we really need to think about the fact that now, in going from that simple extension of the model, we've actually opened up lots of additional relevant aspects to the modeling approach. And Higgins, Thompson, and Spiegelhalter have really listed, they've categorized these into 5 different relevant aspects of random effects modeling. The first is a quantification of the heterogeneity in the results. That is to say, how much between study variability is there in those results. So that if you think about it, that they're saying the most important thing is tau squared or I squared. The second thing is the estimation of the mean effect. So that's theta in the model that we were just looking at. The third is estimation of study-specific effects. So as you can imagine, we can, just like we can in population modeling, we can get individual predicted estimates of the true effect within each of these studies. So that would be estimates of the theta i's. We can use that model to get predictions of the effect in a new study. And that's going to rely on the sampling distribution of the theta i's, as well as some measure of residual variability or sampling variability for the new study. And then the fifth element is testing. So whether or not we can test whether an effect exists in any particular study. We can assess whether there's consistency in the direction of the effect. And we can look at whether an effect is predicted to exist in a new study. So if we were going to perform a new study, what does the model give us in terms of a probability that we'll see or a distribution for the effect in that new study. And depending on your particular meta-analysis approach, you may have all of these aspects may be relevant to your modeling exercise, or only some subset of those. So in that same paper, the authors give the following recommendations. They suggest always use a visual inspection of a plot, such as a forest plot, to give us sort of an initial idea about how much heterogeneity there is. And then the second is to allow for heterogeneity in a meta-analysis, either by using covariates to model that heterogeneity, or simply by putting in random effects, or both. The third is to interpret these models with the appropriate consideration of the fact that we have a distribution of effects. So not simply presenting a confidence interval, but in addition to presenting a prediction interval. And then fourthly, to focus your statistical tests on important questions of whether an effect exists anywhere and whether it has a consistent direction across studies. I've given that a lower priority here because really our focus in this class is on estimation and not so much on testing. But if you're thinking about using meta-analysis to perform statistical testing, then that may be one that's of interest to you. And I would refer you to the original paper. So my feelings are that we should always, because we should expect there to be some heterogeneity, we should always begin with random effects models. While the fixed effects models give us a nice background and a good starting place to learn about these things conceptually, really there's no reason why we shouldn't always be fitting random effects models. And one of the reasons is because if there is very little or no between study variability, then the random effects estimator collapses to that fixed effects estimator. And so just to show that real quickly, if we come back here to our random effects estimator, if this estimate of tau squared is in fact equal to 0, then the random effects weights simply are 1 over the SI squared, which are exactly the same as the fixed effects estimator weights. So if tau squared is equal to 0, the random effects estimator becomes the fixed effects estimator. If tau squared is small relative to the SI squareds, then you get something that's essentially the same or very close to the fixed effects estimator. So there's really no benefit to doing that fixed effects approach. In addition, using this random effects structure really gives us that natural way to make predictions about future studies. And if we're simply thinking about this as a bridge to getting to more complex model-based analyses, it's a natural segue between the random effects models here to the kinds of random effects models that we'll get to when we talk about model-based approaches. And lastly, and this is a subtle point and one that people often ask about, is that when we fit random effect meta-analysis models, you'll see in the examples we get wider confidence intervals. What's interesting about that is those are really more of the correct width confidence intervals than you get from a fixed effects model. The fixed effects model is assuming there is no between study heterogeneity, and as a result, you in some sense have more information than you do, or the model is assuming you have more information than you really do, if there is between study heterogeneity. And interestingly, there was a review by Chris Schmidt and colleagues in 2009 that compared fixed effects analyses versus random effects analyses, and they looked at the nominal coverage of 95% confidence intervals, and they were able to demonstrate that really on average those nominal 95% confidence intervals from fixed effects models only had about 56% coverage, as compared to the nominal 95%. So that tells you right away that those fixed effects confidence intervals are too small. So again, that's another reason for moving towards random effects models, to get kind of the correct width and the correct coverage, or the expected coverage of those confidence intervals. There is a problem though, in that if we're doing an analysis and we have a small number of studies, we have a little bit of an issue, because we're estimating this between study variance component here, going back to the model, tau squared. If we only have a handful of studies, we're estimating that variance from a small number of samples, small number of observations, and that can be problematic. It's just like as if you're just simply calculating a variance based on small numbers. Your uncertainty in that variance is large, and as you can see when we're calculating the variance of our random effects estimator, we're conditioning on tau squared being known. So we're plugging in some estimated value of tau squared. We're not actually accounting for the uncertainty in tau squared in our confidence intervals, even for the random effects estimator. So when we have a small number of studies, random effects models, random effects meta-analysis models can be problematic. So the question is, what should you do in that situation? Well, you need to make a choice. You can either say, well, if I have a small number of studies, I'm just going to move to a fixed effects analysis. And that doesn't seem very satisfying. It doesn't give you this nice way to generalize into wider populations, or to get predictions for future studies. And we know that the confidence intervals are biased. Probably a more principled approach, or the approach that we would advocate, would be to take a Bayesian approach. In that case, though, that's not a panacea, because we still need to put in some information through the prior about tau squared. So we'll need to put in some kind of moderately informative prior distribution on tau squared. And some people may object to that. And then the last approach is to simply just not do the meta-analysis at all, just to simply say, well, I don't know what the effects, I can't get an overall average effect, so I'll just report those results from those handful of studies separately. And you do sometimes see that, see authors reporting meta-analyses in that way when there's only a small number of studies. I think going, really our recommendation would be to, or my recommendation would be to fit a random effects model. If you don't have enough studies to get a precise estimate of tau squared, to consider moving to a Bayesian model, if you haven't started there in the first place. So let's come back to that LDL data. We had, a few slides ago, looked at the Cochrane's Q statistic, which told us there was statistically significant heterogeneity. With the I-squared statistic, we saw that there was about 55% of that heterogeneity was due to between study variability. But let's go ahead and say fit the random effects model to those data. So I restated the model here in the middle of the page using slightly different notation. My apologies for that. Where I'm using μi here to represent the study-specific mean response in the ith study. And the mui's then are distributed with a mean of, normally distributed with a mean of theta and a between study variance of tau squared. So we had from our fixed effects analysis, remember we had our Q statistic was 15.61. I didn't show it to you before, but trust me that the sum of the fixed effects weights was 1.684, and the sum of those squared weights was 0.804. And plugging those into the formula for the DerSimonian and Laird estimator, we would get an estimate of tau squared of 7.13. And given that, then we can plug into our equations to get the random effects and the estimator and the variance of that random effects estimator. And if we do that, we get the random effects estimator is minus 37.82, and the variance of that is 1.36 squared. So we can get an approximate random effects confidence interval estimator going from minus 40.49 to minus 35.16. So you might be asking, how do those compare to what we did with the fixed effects estimator? And if we were to plot them on the same forest plot, the top of the panel here is the same 8 studies and the data that we had before. This red triangle down here is our fixed effects estimator, and the black diamond is our random effects estimator, or the confidence interval from the random effects analysis. So we see that the 2 parameter estimates they're similar. Minus 37.8 from the random effects analysis and minus 37.2 from the fixed effects analysis. But that the confidence interval from this random effects analysis is wider. So we see in this particular case, there's really not much difference between the two in terms of the average effect. Now, what I haven't done here is shown a prediction interval for a future study, but within this context, it would be easy to do, and that will be part of your homework assignment. So now what we're going to do is we'll switch gears a little bit, and we'll move to using metaphor and WinBUGS. That's another typo. Should be WinBUGS for fitting a random effects meta-analysis. And as I'm pulling that up, I'll just give you an opportunity to ask any questions that you might have about anything we've covered so far. So we have one question. If using the Bayesian approach, can I get versions of Q, I squared, or H? That's a good question. Let me think about that. Let's pull up the slides again. So all of those rely on some measure of variability. You could certainly get an I-squared estimate. I'm not so sure about Q. Let's go back to our viewer here. So here's our Q statistic. Q is depends explicitly on that kind of fixed effects estimator. In order to answer that question more thoroughly, I might want to go back to the original source literature to talk about where they derived this from. But I would say, in general, you're not going to see a Bayesian equivalent of the Q statistic. However, you can imagine getting a Bayesian estimate of I-squared in the sense that in the random effects model, in the Bayesian random effects model, we have explicitly tau squared in here. And in fact, to come up with an estimate of sigma squared, you can imagine taking an average of the SI squareds or something analogous to that, and coming up with a Bayesian equivalent of the I squared statistic. And falling out of that, then you could get kind of a Bayesian credible interval for the I squared statistic. So I would say yes for I squared, possibly yes for H. The way I've expressed it here, H is a function of Q, but in fact, there's an equivalent representation of H as a function of I squared, so or I squared as a function of H squared. So I think you can conceptualize how that might play out in a Bayesian setting. And maybe we'll come back and try to give an example of that during the hands-on session on Monday. Okay, so what we'll do next is we'll step through the material that I posted to the course site earlier this afternoon. I have a little file there that's called Introduction to Metaphor.R. And Metaphor is the package that we'll be using to do all of the simple traditional meta-analyses. It's actually a very good package. It can be used for making forest plots and other kinds of graphical displays of meta-analysis data, as well as fitting fixed effects and random effects meta-analyses and meta-regressions that we'll get to next session. So I'm going to go ahead and open up my that file here, and rearrange my screen a little bit to make things viewable, hopefully, for you. So we're going to first load. Let me try and make my font bigger. I can get the console bigger, but I'm struggling here to get the script itself any bigger. I apologize for that. So we'll hope that you can see it clearly enough. First, we'll load the metaphor library. In addition, I'm going to load two other libraries: the R to WinBUGS library, which we'll use for fitting our Bayesian models, for calling WinBUGS from R, and the EMD book library, which has a particular helper function that's going to be useful when using the output from bugs. So we'll run each of these lines here. So we've loaded metaphor, loaded R to WinBUGS, and we'll load the EMD book library. You'll need to set this, if you're using this as this script as a tester, you'll need to set this to your wherever you're running your local installation from. I'm running it off of my my E drive. And in the MI260 folder, and within that, in the fixed effects hands-on subfolder, there's a data set called Atorvastatin studies. And this is a data set that we'll be using later on in the course when we look at some model-based approaches, but we're going to use a subset of those data, the 10 milligram atorvastatin versus placebo, to sort of replicate the analyses that we performed for in the slides. So here I've read in that data set, and I'm showing you what kind of the top of the data set looks like. Within each study, we have within the data set, we have variables for trial, drug 1 and drug 2. These will be relevant when we get to the model-based modeling, but for our purposes, we'll be focusing here on drug 1. Corresponding values for dose 1 and dose 2. N is the number of patients in that treatment arm. Week is the week at which they were evaluated. And LDL PCFB is the percent change from baseline LDL. That's going to be the endpoint that we're interested in. So let's, in addition, we have the standard error of the LDL percent change from baseline. So we have, for this analysis, the LDL percent change from baseline, the standard error of the LDL percent change from baseline. And we're going to need to do a little bit of data manipulation in order to move this to a point where we can work with, for example, 10 milligrams versus placebo within each study. So that's what the next few lines of code are doing here. We're just doing some data manipulation to first only keep the atorvastatin data, and then to subset out the placebo arms from each of the studies, and then rename those to put a .pbo suffix on the variable name so that when I merge them back together, we'll keep them separate. So here we are merging back in the atorvastatin and placebo data together. And then this little bit of code here calculates the difference in LDL percent change from baseline between the atorvastatin arms and the placebo arms. And then using a simple mathematical relationship to calculate the standard error of the difference as the square root of the squared standard error for the atorvastatin mean change from baseline and the squared error for the placebo change from baseline. Okay. So that's gotten us to a point where we have all of the atorvastatin data, but for our purposes, just to replicate what was done in the slides, we're going to focus here only on those studies that had a 10 milligram atorvastatin dose. And as your homework, you'll be essentially replicating this sort of analysis, but looking at atorvastatin 80 milligrams. So if we look at the trial data, this is here essentially the table that's presented in the slides when we first started talking about these data. So the first thing that we're going to do is to make some plots, some forest plots using some of the functions in the metaphor package. And in particular, the one function that's of most use to us is going to be for making these plots will be the forest function. So the help file for the forest function tells us that where's it going? Tells us that there's kind of two versions to this forest function. One is the forest.rma, which is working off of an RMA object, and we'll come back and talk about that after we talk about how to use the RMA function. And the second is kind of the default version, which is just a version where we tell it the data explicitly, and it goes ahead and makes a plot for us. And so to begin with, that's the version that we'll look at, is this forest.default function. So forest.default takes at a minimum two values. One is the mean data that you want to plot, that's x, and the second is either the variance or the standard error of that, so either the variance or the standard error of the mean value, or the mean effect size. So for our data here, that means we could simply say, well, let's give it, we'll call the force function, we'll pass in the difference, we'll pass in this column here, and we'll pass in the standard error of the difference as our standard error. And if we do that, we get a forest plot that looks like this. This is sort of the out-of-the-box, no frills version. It does a pretty good job of displaying our data here in the order that they appear in the data set. It makes some attempt at putting labels here, just calls them study 1 to study 8. And over on the right, it provides the observed data, the mean, and a confidence interval based on that, the mean and standard error. Of course, if you wanted to, this is fine just for kind of taking a quick look, but you often are going to want to put some more bells and whistles on this by changing the x-axis and putting better study labels on here and maybe reordering these. And so there are lots of options to the forest function that allow you to turn on or off the annotations. The annotations are these elements over here to the right of the plot. You can, if you choose to, show the relative weights. It would insert those as a column of values here in between the plotting symbols and the annotation. You can obviously control, as with most R plots, the x limits and the y limits. You can control where the ticks are at on the x-axis. You can control the level of the confidence interval that it plots. You can control the reference line. I didn't mention it, but here is by default, it puts in this dotted line here, which is a reference line at a value of 0. And those are really, I guess, the main options for this version of the function that you might be thinking about. So we could, for example, make a slightly prettier plot by adding in, giving it an explicit study label. That's the slab argument, and that gives us these somewhat better labels over here. We can tell it ref line equals null or ref line equals NA. It gets rid of that reference line. Or we could explicitly tell it if we wanted a reference line at a different value, we could plug that in there. And then I've just given it better X labels and given it a title. And if you really wanted to control in this version of the forest function the order of these plots, frequently you might see these plotted in order of publication date or in order of effect size. Then you need to sort your data set in that order. So in this case, I'll sort my Atorvastatin and by the size of the difference from placebo, or in the reverse order of the size of the difference from placebo. And then I'll go ahead and plot that here. Again, with a few more controls on my x-axis scale. So that's, I've now added where the ticks are, and the ordering now gives us a slightly more visually interesting plot. If you're interested in adding annotation or in adding the weights, if you did something like show weights equals true, we would end up with a plot that looks like, oops, that doesn't look like that. Show weight, sorry. It looks like this. So we see here, it gives us our what are fixed effects, since we haven't fit a model, fixed effects weights. Okay, and if you want to, by default that's false. If you want to add in headers, for example, on the columns, you need to just simply add those in on your own with text statements. Okay, so the force function, if you just want to plot the data, is a useful tool, and I think that this is a very sort of useful go-to function to use when you're doing meta-analyses. For fitting the models, the function that we'll use primarily from the metaphor package is the RMA function. The RMA function is a real workhorse. It can do a lot of things for lots of different kinds of data. I won't spend much time going into all of the details, but I would refer you to the help file. So if you look through the help for RMA, you'll see that there are, the input to the RMA function. It can take all of these varieties of input. For the example that we'll look at today, we need to specify at least a yi, which is our difference from placebo, and either vi or si. Those are going to help it. Those are the variances or the standard errors again. If you're working with binomial data or Poisson data or hazard ratios or time to event data, there's other options you have here for working with those kinds of data. And in fact, if you're working with continuous data and you don't have the differences in standard errors derived, but you have those separately for the different groups in your data set, you can work with those as input as well. And I'll show you an example of doing that in just a minute. I'll just simply refer you to the help file for the RMA function to get more information about the kinds of data that you can work with and how you might input that. One of the important arguments here, though, is the method argument. By default, RMA will fit a random effects meta-analysis, and it will use the REML estimator of the variance component. If you want to get a DerSimonian and Laird estimate of the variance component, you'll change the method to DL. And if you want to do a fixed effects analysis, you'll change the method to FE for fixed effects. And so we're going to demonstrate that here using our Atorvastatin 10 milligram data. So here this call to the RMA function simply says my response variable is the difference. The standard error of that response is in my data set called SEDIF. Here's the name of my data set. My method is fixed effect. And optionally, in this function call, you can apply a label, a study label, to each of the studies in your data set. And that's just going to be useful for when I make some plots using this RMA object. So if I run that and then look at what the output from RMA is, it looks like this. So by default, it tells me first that I've fit a fixed effects model and I've had 8 studies. It first shows the test for heterogeneity. So it shows us our Q statistic. Remember, we had come up with our 15.61 and a corresponding p-value of 0.029. And then it provides down here the estimates. So here's our estimate of the difference based on the fixed effects analysis of minus 37.2, corresponding standard error of 0.771. And if you're interested in doing a test, it gives you a z-value and p-value. That test is testing whether or not the estimate is equal to 0. And then it gives us a confidence interval. And we can control the confidence level. By default, it's 95%. So that's what we get for for a fixed effects analysis. If instead we didn't have the difference in the standard error calculated, we could plug in the mean response in each of the two groups separately. We'd have to give it a standard deviation. That's not a standard error now, a standard deviation for each of the two groups, and then the sample size from each of the two groups within each study. And then explicitly tell it what measure that we're working with. In this case, the measure we're working with is the mean difference, or abbreviated MD. All of that information is in the help file for RMA, and in particular, when you look under the help file for the scalc function, which RMA calls in order to derive the endpoint. So if we were to fit the model in that way, we can see that we get the same output as before. So again, our Q statistic is the same. Our estimate and standard error and confidence intervals are the same. So we have some flexibility here with how, depending on how your data set is structured, how you can input the data into the function. What's handy is there is a plot method for RMA objects, and so if I were to say plot my FEMA object, what it makes for me by default is a 4-paneled plot, a forest plot in the upper left, a funnel plot, which we'll talk about next session, in the upper right, a radial plot in the lower left, and the residuals in the lower right. In this case, the residuals here are showing some pattern because I've ordered the data set to go from lowest difference to largest, from smallest difference to largest difference, and so that's why there's a pattern here in the residuals. So we don't want to make too much, pay too much attention to that particular plot in this case. And we'll talk about the funnel plot and the radial plot in the next class and how to use those. Now, one nice thing is, again, there's a special method of the forest function for RMA objects. So if we were to plot, simply say forest of this FEMA object, what we get is a forest plot that looks very similar to what we had before with the default plot. But what is added here is a bottom row that gives us our fixed effects estimator as a diamond. Gives us kind of a generic label here called FE model, and it gives us the numeric tabulation of that corresponds to the endpoints in the center of that diamond. And then we can do all of the same things as we did with the default version. We can do the same kinds of things with our RMA object. So if we plot, if we do a forest function of that object, we can take out the reference line. We can add in our prettier labels, and so on. So I'll just show you that here. So this is the kind of plot we can make simply by default from fitting a model in one line and then plotting that object. I'll just draw your attention to the fact that what I've done here when I've made this plot is I've controlled the Y limits, and I've added in an extra couple rows here on the bottom. And I've done that intentionally because there's a function that, let me check something here, that that comes with the metaphor package called add poly, which allows you to add in additional polygons or additional triangles, diamonds down here on the bottom from different model fits. And so in this case, if I wanted to just visually compare whether I get the same fit, whether I use the two different approaches to fitting that fixed effects analysis, I could say add poly, and then provided that other alternative RMA object, tell it where to plot it. In this case, I'm going to say plot it on line -2. I can give it a different color if I'd like, and I can tell it, give it a better label. And so if I were to run this particular line of code, I can update my plot in this way. So you can see, as we would expect in this case, our two approaches to fitting the model give us identical results. Now for this is a very simple toy example, and in just a minute we'll talk about how to fit these models in BUGS, or I guess we'll come back to that during the hands-on or lab session on Monday. But this becomes a very useful way to compare maybe fits versus a classical approach and a Bayesian approach, or between a fixed effects model and a random effects model. Okay, I think that probably brings us to a reasonable stopping place. Why don't we I'll see if you have any questions on the use of the RMA function or of the metaphor package at this point. Like I said, your homework will be using the RMA function to fit fixed and random effects meta-analyses, as well as using the force function to make some plots. So if there's anything that wasn't clear now, feel free to ask or post those to the training site. Okay, I don't see any questions. So what we'll do is I will post the specific homework problems tomorrow morning, and then we'll during the lab session we'll review those homework problems. We'll step through those together and go through how to fit the Bayesian versions of these models using WinBUGS. If you'd like to, you can get a kind of a preview of how to do that in this Introduction to Metaphor R script. It gives an example of how to fit those using R to WinBUGS, and the two Bayesian models were also attachments that were posted to the course site. So if there aren't any other questions, then I think we'll end there for the day. And again, feel free to post any questions you have as you're going through the homework to the course site. Thanks a lot.